How is everyone doing? Awesome, right? Good. Online people, can you see my screen?
Yep.
Yep, good. Okay. Chapter 6, fun chapter. Learning reactions. We have 2 mechanisms under our belt already, and a few more to come. We talked about Sn1 and Sn2 in great detail over the last week or so. Right? We talked about Sn2 being one that looks like this, where you have a nucleophile. Let me pick a nucleophile. Let's pick Cl- as our nucleophile. And we're going to pick our substrate to look like this. Our leaving group will be something great like iodide. It's a good leaving group. We have nucleophile attack, leaving group leave. In one step, we have Cl like this, plus I minus. This is an Sn2. Sn1 was similar, except Sn1 had 2 steps. Basically, the same action happens, but in 2 discrete steps. So this would be something like this, same nucleophile, but let's pick a tertiary alkyl halide. The last one was a methyl. And what happens here, first of all, is the leaving group leaves. To give you a carbocation, which is tertiary. And then once that leaves, the nucleophile can come in and give you Cl. So these are the 2 basic mechanisms we looked at. Sn2 is 1 step, bimolecular rate determining step. Sn1, 2 steps, unimolecular rate determining step. Sn2 is favored by polar A product solvents. Talked about that a little bit. So Sn2, good solvents are things like acetone, DMSO, DMF, acetonitrile, etc. Whereas for Sn1, because these are better with a product solvent, like water, alcohols, carboxylic acids, amines, things like that. And the reason is that product solvents can hydrogen bond to ions and stabilize ions. And because the rate determining step in Sn1 is making an ion, it's easier to make it in a product solvent. Sn2, the nucleophile is stabilized because it's an ion, often. It's stabilized by a product solvent. And you don't want to stabilize your reactants. You want to destabilize your reactants and stabilize transition states and intermediates. All right, Sn1, Sn2. We also said Sn2 was favored for what I'm going to call unhindered substrates, alkyl halides. So this would be things that are like methyl and primary. Right? So if you have an alkyl halide that looks like this one would be primary, it's easy for a nucleophile to fit in there. Okay? Whereas Sn1 likes stable carbocations, so tertiary is fastest, followed by secondary is okay. So those are kind of the factors that dictate what mechanism happens, right? And if you see a reaction, so if I gave you a reaction that looked like this, and asked you what the mechanism was, you'd have to put these pieces together. You see NaCN, and what's the first thing you should think every time you see sodium? Anything? Yeah, split it apart. NaCN is Na plus and Cn minus. And this is the nucleophile. The sodium doesn't do anything. It just floats around. It's a spectator ion. So this is the important part. If you see NaCN in your brain, you should think Cn minus. That's a nucleophile. Look at the substrate. What kind of alkyl halide is this? Primary, secondary, or tertiary? Yes, primary. And what mechanism is best for primary? Yeah, Sn2 is best for this. What about our solvent? What kind of solvent is that? That's one of our polar aprotic solvents. So that's good for Sn2 as well. Everything here is screaming Sn2. Sodium cyanide is a great nucleophile. Strong nucleophiles also favor Sn2. How do we know it's strong? It's got a negative charge. Okay. I'm getting a phone call. Nope, can't answer it. Yeah, here's my wife. Yeah, so let's do another one. What if I gave you something like this? Okay, so what is our starting material here? Which alkyl halide is this? Primary, secondary, or tertiary? Yeah, this one is secondary. So secondary Sn2 or Sn1? It's one that can go either way. So we need to look and see what else we have going on in our situation here. Do we have a strong nucleophile? No strong nucleophile, which means Sn2, it kind of likes strong nucleophiles. What's our solvent? It's polar protic. Polar protic. It's water. Water's our solvent and our nucleophile. So polar protic is best for what kind of mechanism? Polar protic, Sn1. Yes, it stabilizes ions. So everything here would scream to me Sn1. Okay. At the end of last class, we looked at an example. I forget the exact molecule, but we can take something like this, primary alkyl halide. And remember we learned how to label the carbons? We said the carbon with the leaving group we could call an alpha. And the one adjacent to the alpha called beta. And so the number of betas is equal to whether it's primary, secondary, or tertiary. So we say this one's primary. We saw an example where if you draw in the hydrogens on the alpha and beta carbons, where we use a specific nucleophile, or I'm going to call it a Lewis base. Lewis base and nucleophile are kind of synonyms. This is what we call an alkoxide. Alkoxides are the conjugate bases of an alcohol. You make it by taking an alcohol, like ethanol, reacting it with sodium metal. That will make NaO plus H2. I guess we need to balance that. And so this thing here, there's a sodium on there, so the immediate thing we should be thinking is let's separate the sodium apart, and we get Na plus O minus, like that. So we get this thing, right? We put that in our reaction mixture. And what we said last class is you get a different kind of product if you do this. You don't get substitution. You get a different reaction called elimination. And in particular, what you get is something like this. What's going on there? We might have predicted, with our knowledge up till today, that this would just be a nucleophile. Attack there, and you get an ether. But no, that's not what happens. You get, I mean, you may get a little bit of that, but you get mostly this alkene. This is not a substitution reaction. This is what we call an elimination reaction. So sometimes you have this other reaction that's competing. And when you get that other reaction that competing is typically when you have a base present. So you can see here we have a base, it's a strong base. Where most other nucleophiles, like I think above, what do we use? Chloride as our nucleophile up here somewhere. Yeah, chloride is a terrible base. One of the world's worst bases. And how do we know it's a bad base? It's because conjugate acid is a super strong acid. HCl is very strong. The stronger an acid is, the weaker its conjugate base. So this is going to be a super terrible base. But a great nucleophile, it's got a negative charge in electrons, so it's fine for that. But alkoxides, alcohols are really weak acids. So alkoxides are quite good bases. They're about the same as hydroxide. And hydroxide we would consider a strong base. In fact, they're a little bit better than hydroxide. Because alkyl groups are electron donating. So they donate to the O- and make it even more basic. All right. So we're going to go back to our slides. This is a particular, yeah, I'm going to come back here. So this thing we would call ethoxide. We can say that this is a primary alkoxide. It's primary because, you know, we have an alpha and a beta. One beta is primary. It came from a primary alcohol, ethanol. If you start with a tertiary alcohol, you can make this, which we would say is a tertiary alkoxide. This is just as good of a base as ethoxide. So this, you know, is similar to this in terms of base strength, but this one is a particularly terrible nucleophile. So this is a bad Nu strong base. This is a strong nucleophile, strong base. So this could potentially do Sn2 or E2. E2, I didn't get there yet. I'm giving away my punchline. Not my punchline. It's not a joke. This is serious business. Yeah. Elimination. It can do substitution or elimination. This thing is really terrible for substitution, though, because it's big and bulky. It's trying to, remember, substitution, it's got to get in there and attack a carbon. And if the carbon especially has like steric bulk on the backside, you know, if it's got lots of groups attached there, it's going to have a really difficult time getting in because it's so large. Whereas this is, you know, thin. It can just go right in, find that little space and go in no problem. All right. So that's alkoxides. We can have primary ones or tertiary ones. You might ask, can you have secondary ones? Yeah, you can, but you'd never use one. You either want it bulky or you want it small. You wouldn't pick a medium one in any case I could imagine. All right, so if you have an alkoxide, we get this elimination reaction instead of substitution. Sometimes you get a mix. So here's an example of terbutyl chloride, right? Bond line looks like this. We're going to do this reaction in 80% ethanol, 20% water, room temperature. And what happens is you end up getting a mixture of substitution products, which you get two different products because we have a mixture of two different nucleophiles. We have ethanol and we have water. And together, that's 83% of your product mix. You also get some elimination. It's about 17%. This is kind of a crappy reaction, actually. You know, if you're in the lab and you're doing a reaction, it's rare that you'd want a mixture of things. Typically, you just want one product. So you'd design this better and pick conditions that gave you something a little clearer. Okay. So how does this work? What's going on in these particular cases? Okay. So in the case where you have an alkoxide, let's go back to our example that's here. Br, it's primary. We're going to label our alpha and our beta. We're going to put in our hydrogens on our alpha and our beta. And we're going to add in our alkoxide that we talked a little bit about so far today. Make it small, make it big, whatever. Let's make it big. So we want this to do elimination. And that's a base. And what do bases want? They want protons. Bases want to grab H plus from something so that they, well, in this example, become neutral. And they want to become their conjugate acids if they're strong bases. And this molecule has a bunch of protons on it. It's got hydrogens all along the chain. So what alkoxides can do is extract or remove a hydrogen on a beta carbon. So what this is going to do is come over here and form an OH bond. Okay. What happens is that CH bond then breaks. You've broken that CH bond, and those electrons will come down here and make a carbon-carbon multiple bond. It'll make the pi bond. Then your CBr bond can break, and bromide comes off. And what happens now is you have this molecule like this. So this is what these alkoxides will do, is they remove a beta hydrogen. And when it removes the beta hydrogen, the leaving group leaves at the same time. The double bond forms at the same time. This happens in a single step all at once. This reaction is called elimination. So the symbol that we give this reaction is an E for elimination. Just like substitution, we had Sn for nucleophilic substitution. Do you think this should be E1, E2, E3? What number do you think we should give this? Look at the reaction. Single step. What does the 2 refer to in Sn2? Bimolecular, yeah. Is this bimolecular or unimolecular? How many things come together in this step? 2. Right? We have our base, which is 1, our substrate, which is 2. 2 things collide. Those bonding changes happen. You have 3 products. But what matters is how many things come together. So we call this reaction E2. All right. We would say this reaction is concerted. Concerted just means everything happens all at once. All the bonding changes happen in a single step. Concerted is the opposite of stepwise, right? So if you had a staircase and you walk down the stairs, That would be a stepwise process. If you jumped off the top stair and landed on the bottom, that would be a concerted process. Everything happens all at once, a single jump, single leap, a single flurry of activity in this case, because lots of bonds break and form. Right? We've broken 2 bonds and formed 2 bonds. So that was 4 bonding changes that all happen simultaneously. Great. Now, you can do, I'm going to come back to that. I keep switching back and forth before I'm ready to stop talking about this. E2 doesn't care if it's primary or tertiary. Why would it? It just needs a beta hydrogen it can get at. Okay, look at this example. We have alpha, beta, beta. How many beta carbons does this molecule have?
Four.
Doesn't have 4. It doesn't have 2 either. 3, because it's got this one. It's tertiary, right? This is a tertiary alkyl halide. That's got hydrogens too. You can draw them in. Well, this is a tertiary alkyl halide. Sure, we can take an alkoxide, in this case methoxide, and it just comes in and it grabs a beta hydrogen. And makes methanol as well. So it doesn't matter for E2 if it's primary, secondary, or tertiary. It needs to have beta carbons with hydrogens. That's all you need for E2. So not every alkyl halide can do that. How about this alkyl halide? Can you do elimination here? Well, we have an alpha. No beta though, do we? No beta carbons here. That means no E2. Think about it. E2 always makes an alkene. It always makes a carbon-carbon double bond. If you only have a single carbon, how are you going to make a carbon-carbon double bond? You're not. You can't. So that's what you get with E2. So in this case, if you do a reaction like this, in this case we have a tertiary alkyl halide, and you do it without an alkoxide. We're going to not put in a super strong base here. And we're just going to put in something like, I don't know, ethanol, which is that. Protic solvent. Protic solvents are great for ionizing things. This can lose a chloride, make a carbocation. It's solvated because we have a protic solvent. Solvated just means there's a solvent shell around it, stabilizing it, keeping it nice and happy. This looks like the first step of Sn1, doesn't it? Sn1, leaving group leaves, and then you get this cation. If you look at this too, we have an alpha, a beta, and a beta. Okay. So with substitution, this is what would happen. For Sn1 substitution, we make that carbocation with the leaving group leaving. Then we have a nucleophile contact. And this Sol OH, that's just like HOH if it's water, or CH3, CH2OH if it's an alcohol. Sol is just the other part of the molecule. And the nucleophile would have a pair of electrons from that OH attack. And then you could lose a proton in a second step, and you have substitution. You have either OH there or OCH2CH3. That's Sn1. That's what we would have seen at the beginning of the chapter. But what can also happen now, alpha, beta, beta, is the solvent can instead decide to remove a beta hydrogen and make an alkene. This is an E2. E2 needs a strong base. E2 is everything happens at once. We call this one E1. Why E1? E1 because the rate determining step is unimolecular. I'm going to write this out more fully over here. And let's give it ethanol. And we're going to heat this thing. This little triangle means heat. Okay. What happens is we have a product solvent and we got heat in here. Those are recipes for ionizing tertiary alkyl halides. We might predict Sn1 here. This would leave that, and bromide goes off on its merry way somewhere. Now we have this carbocation. It's stabilized by the solvent, but the solvent can then come in and attack. It can be a nucleophile. It's a much worse nucleophile than bromide, but there's a lot of it around because it's a solvent. So what happens here? So one of those lone pairs makes an CO bond. The second lone pair stays on the oxygen, and we get a positive charge there. So this is it. That's the substitution. There's another quick step to make this neutral. We'd like to make our products neutral. And what we can do is use another molecule of solvent to come in as a base to remove that H+. All right. And then that kind of goes away somewhere. Where does it go? Away. All right. So this is E1. It has two steps. The E1 part has two steps. It has the first step, which is formation of the carbocation, loss of the leaving group. Second step is loss of beta hydrogen. So this is just like E2. E2, you lose the beta hydrogen, the double bond forms, the leaving group leaves all in one step. This is the same process except broken into steps. Okay. Where the leaving group leaves first, and only then, after you have a carbocation stick around for a little while, do you then do the elimination step. So what we're going to do is we now have these four competing mechanisms, Sn1, Sn2, E1, E2, and under certain conditions, you'll get a mixture of more than one mechanism. Under other, if you control the conditions right, you get just a single one of these four processes. Two of these processes give you alkenes. The other two give you substitution products. There's a difference between Sn1 and Sn2 sometimes in the products you get, because Sn2 inverts the stereocenter, Sn1 doesn't, or you get a mix. It's a stereocenter. So it's now in this course that many people start to feel like you just gave me an overwhelming amount of information, and I'm still trying to figure out the difference between what happens in each of these four mechanisms, and now you're telling me they all kind of happen competitively, and you know, in a certain situation, you could have more than one of these going on at the same time. That's all true, but it gets easier from here. Okay? Until we get to next chapter, but don't worry about next chapter. So what I want to do is break down for you when each of these reactions can take place. So our starting compound can be either methyl. So this means, you know, your X. This is going to be your leaving group. It can be methyl, it can be primary, it can be secondary, or it can be tertiary. So let's make a little table. All right. So this is going to be the identity of our nucleophile base down in this column. So our nucleophile base, think about, first of all, we're going to have, this is going to be our options. Alkoxide, like that. Actually, I'm going to make it like this. This is going to be a bulky alkoxide. Bulky alkoxide, small alkoxide. Bulky ones are tertiary, small ones are primary. Negative nucleophile is the next one, like chloride, iodide, cyanide, azide, sulfide. If you checked out the Instagram, there's a new table with all the nucleophiles that we use. It breaks down which ones are strong, which ones are weak. So we'll just say strong nucleophile here. Or none of the above, but you have a product solvent, like water, alcohol, something like that. All right, so we want to know what mechanism is going to happen for each of these. So what do we have? 16 squares. So you got to memorize 16 different sets of conditions. But you don't memorize. We don't want to memorize anything in this course. What you want to do is understand. We understand a lot. So what we do understand about methyl is you can't do any elimination on a methyl, because you need 2 carbons minimum to do an elimination, and methyl just has a single carbon. So this would be something like CH3Br, something like that. This would be like this, and this would be. So methyl will always do substitution. Will it ever do SN1? No. Methyl will never do SN1 because SN1 requires a carbocation to be formed, and methyls can't make carbocations either. So methyl doesn't have a whole lot of choice here. No matter what, methyl is going to do SN2. Okay. Alkoxides, they're really good for elimination. They will do elimination on primary, secondary, or tertiary by E2. Looks like 16 blocks, but we don't really have 16. We kind of have, we have a smaller number than 16. Right? Small alkoxides are also good for E2. It's filling up very quick. Why do we give small alkoxides even its own category if they all do the same thing as bulky alkoxides? I'm going to just because down the road I'll want to have made that distinction. Okay. Negative nucleophiles that are not alkoxides won't do elimination. They do substitution. So a strong nucleophile wants SN2. And it'll do SN2 if it's methyl, if it's primary, if it's secondary, but not tertiary. We said tertiary doesn't work by SN2, so that one's going to be SN1. And we don't have any of the above. We have nothing negatively charged in there at all. We just have a neutral solvent like water or ethanol or something like that. The solvent then is going to be the nucleophile. It's going to be a weak nucleophile and a weak base. So what are we going to do? Well, for a primary, primaries do primary. So E2 is going to be off the table for all of these because you need a strong base for E2. So no E2 on the bottom row. So that primary alkyl halide, if it's not going to do E2, can it do E1? No. No E1 either for primary because you need to make a carbocation for E1. Primaries don't make carbocations. So all these little pieces of information you've learned as one-offs, we're fitting them all together now into this big grid. We're trying to understand how all of these molecules might react. So E1 is off the table, Sn1 is off the table, because no carbocations for methyl or primary, right? This whole block right here can't have any carbocations, so E1, Sn1 off the table for all of those. It's all between Sn2 and E2. E2 if you have the alkoxide, otherwise Sn2. Great, so let's put our Sn2 in here. Sn2 is our only option. Not a great option, but you don't have a strong nucleophile, but that's all you have. Can't do Sn1, can't do E1, won't do E2 without a strong alkoxide. All right, now we're getting into the muddy territory. We have secondary and tertiary. These can form carbocations, so these can do E1 or Sn1. They're not going to do E2 because you need an alkoxide. We don't have an alkoxide. You need a strong base. We don't have that. So we would say in this situation, for a secondary, Sn1 under those conditions is better than Sn2 because we have a product solvent to stabilize the ions. We have no strong nucleophile, which favors Sn2. So Sn1 is really kind of what we're looking at here. But you can also get E1. Tertiary, you're not going to get Sn2 or E2 either. So here's something. Whenever you get Sn1 with alcohols or product solvents or things like that, if there's no strong negatively charged anything in there, you usually get a mix of Sn1, Sn2. Sorry, Sn1, E1. Which is why when we're designing reactions, we want to avoid conditions that produce mixtures. So you'd pick one of the other blocks. Because you don't have to use Sn1 or E1. You could pick a different block, and instead of using water, throw in hydroxide. Get a really strong nucleophile in there, and then steer it a different way. The other little bit here I wanted to add in is E1 is, in fact, any elimination reaction is favored by heat. So if you have an Sn1 E1 mix, if you raise the temperature, you're going to get more elimination. You know, the ratio of the products is going to shift towards elimination. So that was like a lot of information. That's the summary of chapter 6. If you come out of chapter 6 and you know this table, you're good. That's not hard, right? Methyls, all Sn2. So we can forget about methyls. We can take that whole row off the table. It's all Sn2. And what do we get? Alkoxides, all E2. Now we can take alkoxides off the table. And then really what we're zooming in on is this piece here where there's some variability. But once you get this down and once you understand the reasons behind why each of these blocks is as it is, this actually becomes pretty straightforward. This is the easy part. And the slightly more difficult part, but still not so bad, is then drawing what takes place. So let's apply this. We've got a couple minutes. Let's apply this. Let's use this alkyl halide, and we're going to treat it with these conditions, and we're going to heat it. What's going to happen here? Well, we could, first of all, we need to look at our alkyl halide, decide if it's primary, secondary, tertiary, or methyl. And how do you do that? Well, alpha is the one with the leaving group. Count your betas. 2 betas mean this is secondary. Great, we got a secondary alkyl halide here. What are the conditions? Is this a nucleophile, an alkoxide? What is this? Yeah, this is an alkoxide. Remember that sodium isn't there. Well, it's there, but remove it in your head. What we're looking at really is this. Think of it as being similar to hydroxide. And if that's the case, we could go up to our trusty old table here and realize that secondary and alkoxide is E2. Or you can reason it out, deduce it. You have a strong base. Strong bases favor E2. All right, so how do we draw this out? Well, you draw in your beta hydrogens on your original structure. You take your base. The nice thing about drawing these mechanisms is every single is the same. Once you've decided what the mechanism should be and then start drawing it, every single example will look exactly the same. You're always, for E2, going to remove a beta hydrogen, make a double bond, and kick out the leaving. You can change the leaving group from iodide to bromide or chloride or whatever. Doesn't change a thing. Still the exact same steps you're going to follow every time. So what happens is the base comes, removes a hydrogen from the beta carbon. The CH bond, the pair of electrons, moves to make a double bond, and then the iodide leaves. So all in one step, you make a double bond. You have one hydrogen left here. You have one hydrogen left there because there's a hydrogen in back. Plus, you have your alcohol and, oh yeah, you have your iodide still too. It now has 4 lone pairs and a negative charge. Cool. All right, let's pick a different example. We'll draw another one out. Let's say you have this guy. All right. Nash. What's Nash? Basketball player, Steve Nash. It's not what I mean. What do you see when you see Nash? You don't see the sodium, do you? Sodium's gone. It's SH minus. Is that an alkoxide? No. Alkoxide. It's a strong negatively charged nucleophile. What about DMSO? What's that? DMSOs are solvent, right? What kind of solvent is DMSO? Polar protic or polar aprotic? Aprotic, which is really good for what kind of mechanism? Yeah, Sn2. So let's see what we got. Our starting compound there, what kind of alkyl halide is that? We've got 1 alpha and 2 betas. We would say this is what? Yep, secondary. Good. So let's go up, see what we got for a strong nucleophile and secondary. Strong nucleophile and secondary up here at Sn2. Great. No pesky elimination to worry about. How does Sn2 look? Nucleophile attacks the alpha carbon, bond breaks. Same thing every time. Our nucleophile comes in and attacks the carbon. Leaving group goes. One step. There. Did I draw that right? No. There's a mistake there. Who can pick out my mistake? It's a subtle one. I'll give you a hint. That's a chiral center. What happens when you do Sn2 on a chiral center? Remember?
Doesn't it invert?
Yeah, it inverts, it flips. So that's not what we got. We didn't invert anything there. We just drew it the same way we saw it at the start. Let's invert it. I don't want pink. Inverted looks like this. There, now it's inverted. So it went from over here, which was S, to over here, which is, wait, that's S. Yeah, that's R. So yeah, because this was Sn2, we have to take care, if you have a chiral center, to flip it. It inverts even if it's not a chiral center, but if it's not a chiral center, there's no difference if it flips or not. All right. We got time for one more. Let's do an ugly one. Because sometimes you get ugly ones. Here's an ugly one. Okay. So what kind of alkyl halide do we have? Primary, secondary, or tertiary? Good. Secondary. 2 beta carbons. Here and here. Do we have an alkoxide? No. Do we have a strong negatively charged nucleophile? No. Are we left with polar protic solvent? Yeah. Okay. Polar protic solvent, secondary. Back to our chart. That's the bottom row. Oh, we got a mix. Sn1, Sn2. We don't like mixes, but you get what you get. And you don't get upset. Anyone know that book? I forget what it is. It's a kid's book that I read my kids like 1,000,000 times, so it's in my head. All right. So we're saying Sn1/E1. That means we've got to draw this twice. We're going to draw the Sn1 and the E1. Well, fortunately, Sn1 and E1 have the exact same first step, which is, what do we form first as the rate determining step in Sn1 and E1? Yeah, carbocation. We lose our leaving group. Gone. There goes the chloride. The yeeting group, we called it, right? Let's draw in all our hydrogens on the alpha and the beta carbons. This is the rate determining step. Now we get 2 different possible reactions. I'm going to redraw it over here. This will be the Sn1 channel. This will be the E1 channel. Sn1, we have our nucleophile attack the carbon. The nucleophile is the solvent. It's a weak nucleophile because it's neutral, yet it's a nucleophile all the same. It can come in and attack the carbon like that. And where does that lead us? Well, that hydrogen looks like this. The nice thing about these is once you can like see how they're done, every single example is the same. There might be extra methyls or slight variations, but they'll all look almost identical. And if you look at all the old tests and midterms we make you draw mechanisms, but like you'll see small variations of the exact same questions just again and again and again over the past years. That's good. We're kind of done, but we need to remove that H+. We want to keep our product in a neutral state. So what we're going to do is bring in a second molecule of solvent. There's lots of it around, right? Probably 1,000 solvent molecules for every starting material. This can act as a base, and you get that. And typically with organic chemistry, we often are a little lazy. We don't draw balanced reactions all the time, every step. We kind of drop things off as we go that don't matter. Like this case, we just brought in this solvent. Where was that at the beginning? Well, it's there, but we didn't draw it. We have to draw and preserve the organic molecule part all the way through. But like chloride fell off in the first step and we never saw it again. It's in there for sure, but not involved still in the reaction. We typically stop drawing it in at every step. Okay, so that's Sn1 substitution. We've substituted the chlorine for the alkoxide piece, which makes an ether. Now this one we said was going to be E1, and it removes a beta hydrogen. The CH bond makes a double bond. Get an alkene. Still have one hydrogen here and one hydrogen here. You could pick the other beta, like there's 4 beta hydrogens to choose from here. You can pick any one of those, it doesn't matter. Plus, I guess you have a molecule now of this, but that floats away. We don't care about it. What we care about is the organic part, what happened to our substrate here. So that's good. That's E1. That's Sn1. What's the percentage going to be at the end of this reaction? There's not a chemist alive who could tell you that answer. We have no idea. You're going to get some of both. It could be 10-90 one way, or it could be 90-10 one way, you know? It could be anywhere in between. What we do know is heat will bump up the proportion of E1. Go higher, higher, higher temp. Okay, if you want elimination, heat it up. That's something we do know, but still we don't know, we can't predict what the percentage would be. Who that's like is their total specialization is like knowing for reactions like this exactly, and like, but no, chemistry is still fundamentally an experimental science. You'd have to do it to see what you get. Why? Last point today. I think we're over time. Quick. Why does heat give you E1? Because if you look at it, two particles goes to 3 particles. So the entropy of this reaction has a positive delta S because you're creating more particles. So if you look at delta G, if delta S is positive, then the delta G is going to be more negative. So it's going to be favorable as you bump up the temperature. As the temperature gets higher, this piece gets more negative, and the reaction becomes more favorable. For Sn2 or Sn1, I guess you have this, right? 2 goes to 2. So that means delta S is going to be small, very close to 0. Temperature doesn't really make this, it'll speed it up, but it speeds up the elimination more. The elimination benefits a lot more because it produces more particles and you have a greater positive delta S. So yeah, that was the explanation for why heat helps elimination in like 1 minute. I timed it. All right, we're over time a little bit, so we're at a very nice time in the course. We're done with chapter 6, ready to go into chapter 7. And And chapter 7 really elaborates on what we've already covered in chapter 6. It introduces a couple of neat angles. So goodbye, everybody.